The problem of adaptation.
Feature extraction, creating artificial agents.
Evolutionary computing.
The evolution of antibiotic resistance.
The use of evolutionary algorithms for optimization.
The microbial system is bacteria.
Biometric recognition.
Microbial evolutions.
An evolution of intelligence.
Microbiology.
Histone deacetylases.
The Beacon Center is a collection of scientists and students working on studying the process of evolution as it occurs. So evolution and action are the key words for Beacon.
What that means is basically studying evolution in real time.
Evolution is not just a process that occurred over millions of years, but something that we can observe.
We can look down on this process as it happens.
So actually seeing how evolution plays out in real time among a variety of different systems.
But it's hard to watch the process of evolution in most systems. You know, human generation, 20, 30 years, elephant generations, maybe even longer.
So it has components from experimental evolution using bacteria and other organisms, and components from computer science where evolution is performed inside of the computer.
So the computer scientists can actually validate their computer models in real biological systems, and biologists can actually speed up the course of evolution.
This is really useful on both the research front and the education front.
We have 4 partner universities: Michigan State, North Carolina A&T State University, University of Idaho, University of Texas, and University of Washington.
We found those where a lot of work on evolution and action was going on, including some collaborations already with MSU.
That grouping of 5 universities has brought together some of the greatest minds in evolution, some of the greatest minds in engineering, and some of the greatest minds in biocomputation.
Often this kind of hidden behind the scenes of how our machines and our computers and all of this works, some of that has been designed by these evolutionary algorithms already.
We have examples of companies that we work with where we can help them to avoid building things, crashing them, testing them, and instead they can do a lot of these experiments in the computer using evolutionary computation tools.
There's a whole suite of challenging problems that we'd love to just turn over to computers and have them solve for us.
Using biologically inspired processes, you could generate products that perhaps would be nearly impossible to envision going at it from like a building block step up.
So that's where the evolution computation also falls in. It's you set up an environment where your agents are, and then evolution tries to optimize these behaviors so that they behave intelligently in the environment.
Anything that you have a good simulation of, you can evolve.
We're starting to see cases where evolution does it better than we can do.
The enamel on the teeth of spotted hyenas is essentially crack-proof because the hyenas are constantly chewing down on very hard things.
I'm talking to a biologist, and there is already, nature has solved it in some way, and I can see that, and I can then go back and implement that idea.
You can evolve parts to cars, you can evolve new antennas, you can evolve components of thrusters that send probes out into space.
We see really fascinating designs in biology that came about through obviously unthinking processes, and being able to harness that power, harness that evolutionary potential, and apply it to circumstances to our benefit.
The evolutionary process comes up with very interesting solutions that engineers might not have thought of.
Over the next decade or two, we'll see drugs coming onto the market that were actually evolved using evolutionary technology.
The biggest example of evolution in action in bacteria is that bacteria can very easily become resistant to new drugs, and this is a very big problem.
There is a trend for people to focus on approaches that are not just killing the bacteria, but that maybe can help them get rid of these resistance genes so that we can use the same antibiotics that we've been using so far.
Science is so advanced now that no person can be a master of every field.
So the fields have reached the point where we can't go any further being just biologists, and we can't go any further being just computer scientists. We have to work together to come up with new knowledge.
Beacon teaches graduate level courses in computer science to biologists, or teaching evolutionary biology to computer science, so that at my level, the level that I'm most benefiting from, it allows us to communicate with each other.
The ideas of biology, the principles of genetic mutation, competition between organisms, adaptation by natural selection, those principles can be extended into computational realms. And these two fields don't really mix well with each other, except here in Beacon, where we have an absolutely stunning common ground, and that's evolution, which is a process that you can study in the lab, but at the same time you study it from a theoretical point of view.
These partnerships provide an opportunity to view things a little bit differently.
Many times you hear it said that the problem with interdisciplinary collaborations like this is the technical language on each side is different. I don't believe that. I think the question is you have different assumptions about what are interesting questions.
It's not a trivial thing to get past the way that people talk from different disciplines and the fact that you may use similar terms in very different ways.
That's what Beacon is all about, is figuring out ways to put people in the same room. And sometimes that means struggling for a while and talking past each other.
But you still have to be willing to talk to people who are masters of their field, even though you don't necessarily understand what they're saying.
When you get to a certain point in science, you're always collaborating with people at other schools. But with Beacon, it creates a really good infrastructure to foster these collaborations.
This is great that there's excellent people here and in these other institutions.
A few times a year we have executive committee meetings here, and then we have this Congress once a year, and that also is a big factor in making Beacon a coherent unit.
If you share meals, you're part of the same tribe. And if you're part of the same tribe, you're going to be comfortable being uncomfortable with each other, because you have to be able to do that in these fields.
A large number of people have a tremendous interest in science. They want to understand how we came into being as a species. They want to understand the processes behind it. They want to understand how nature works.
Just illuminating all these day-to-day mysteries helps you better understand the world that you live in.
We're not asking, what is the origin of man? We're asking, what is the fate of this bacterium? And how can we use those principles of evolution and solve real-world problems for society?
Things that impact the development of drugs, the development of treatments for disease, understanding issues in the environment, including conservation.
So what Beacon does is it allows for the dollars that are being spent in evolutionary biology to go so much further, because we're combining computer scientists, microbial population geneticist people with, macroevolution ecology people all together.
To actually look at problems, questions very specifically related to humans, and to think about how can we use evolutionary processes to solve those.
Through using evolution, we can design better drugs, medical treatments. We can design better buildings, cars, rockets.
A person's gender or race or whatever, it doesn't really matter. All you really care about is, are the people smart and interested, and can they talk to each other and work together?
One of the great strengths of Beacon, and one of its commitments, is to address people who have been historically underserved by science as a whole, and by evolutionary science in particular.
People with radically different backgrounds growing up, different socioeconomic status, different all sorts of things coming in together.
This diverse set of ideas allows us to do, work that would have been impossible just by isolation.
Being exposed to diversity of thought and perspectives, however those are generated.
Outreach and education are absolutely important, and that's probably our most important mission, because our job as scientists is to help illuminate the natural world.
Doing education, outreach to the general public, to kindergarten through 12th grade education, to undergraduate institutions, and then of course to scientists as well, graduate students, postdocs, faculty.
Everybody tries a little bit by getting students enthusiastic for science and fun experiments and examples and relating it to everyday life.
A lot of science bloggers out there, they're all on Twitter, and
Beacon takes things down to a low level. They communicate face-to-face with students.
About 300 generations in. And which condition is this that they're adapting to?
To teach them about the power of evolution to solve problems of disease, problems in engineering, problems in computer science.
And lots of people in Beacon are developing new tools for showing these processes, which is one of the really strong things.
We have a faculty member at University of Idaho who's developed a software program called Ladybugs and Aphids, and we think it has really great potential for teaching young children, like fourth graders, about evolution.
The museum exhibit that they've made here really just shows how you can watch evolution and some of the processes by watching it happen, which is really powerful.
We have made inroads into K-12 classrooms and undergraduate classrooms taking some of our tools and using them to help people understand how evolution works and that it does work.
The better informed the general public is, the easier our lives become, the bigger the appreciation about things is, and quite frankly, the bigger the funding will be.
I need to reach out to the world and to the scientific community and communicate what I've found. Otherwise, I might as well be playing in my basement. It doesn't really matter.
Beacon's goal, our mission, is not to explain the evolution of man. And we're looking at evolution going on in the world today.
There are biological questions that people are addressing. It might be animal communication, for instance. We can develop theories to understand how bees or hyenas or other animals communicate.
Some of us who started out as students and are now postdocs, or the people who are currently students, progress through the academic tiers. I think we'll have many little Beacon satellite institutions and many more people doing these interdisciplinary studies.
People will have a better understanding of evolution as a dynamic, ongoing process. Evolution is something that's happening all around you, and evolution that takes place in your daily life.
Our approaches solve very serious scientific problems that impact people on a daily basis and will eventually, undoubtedly, improve the standards of life for a wide variety of people.